All right, so let's start. Today, you are going to learn another new chapter, chapter number 9, and it is about static equilibrium and elasticity. So in the first part of this lecture, you will be learning about static equilibrium and then elasticity. So the static equilibrium you already know. So here, you will be learning about some application of the Newton's laws of motion. Okay, so Newton's laws of motion you will be learning here in this in the first part, and then elasticity it's a little bit different. Okay, all right. So here basically static equilibrium basically the Newton's first law, application of Newton's first law. Okay, so if you remember Newton's first law tells us that if net force is equal to 0, okay, so let me write down, if net force F is equal to 0, then an object, if an object is at rest, it will be at rest. If an object is in a motion at constant speed in a straight line, it will be keep moving in a straight line at constant speed. Okay, so that's the Newton's first law. So here we'll be dealing with this. Okay, now here you see that if it is equal to 0, if the net force is equal to 0, it could be either be at rest, okay, or it could be at moving at constant velocity, right? So when the object is at rest, we call it static equilibrium. Okay, and when the object is at moving at constant speed, we call the object is in dynamic equilibrium. Okay, as the chapter name is static equilibrium, you probably understand that you will be just learning about static equilibrium, not the dynamic equilibrium. Okay, so when the object is at rest, the object is called under static equilibrium. So we are going to learn more about the static equilibrium, not the dynamic equilibrium. So the dynamic equilibrium, in dynamic equilibrium, still the net force is equal to 0, but the object is moving at constant speed. Okay, but we are not learning this here, so this cancel. So our focus is only when F equal to 0, the net force equal to 0, and the object is at rest. Okay, all right. Now, what are the example of static equilibrium? So, for example, an object, a textbook on the table, sitting on the table. Okay, so you see that the textbook is at rest. Okay, so you see that there are several forces acting on this textbook. So there is gravity, there is normal force, but the object is at rest. So that means the net force acting on this object equal to 0. So that's why it is at rest. Okay, so some examples are, for example, this is an example. This picture shows an example. Okay, this object is at rest. Okay, so that means this is in static equilibrium. Okay, other examples are hanging sign, ceiling fan, ladder leaning against a wall. So this is a little bit difficult problem, ladder leaning against a wall. Probably we are not going to do that, but hanging sign or ceiling fan, we probably do that. We probably solve some problem. Okay, so these are the some example of static equilibrium. Okay, all right. Now, what are the condition of static equilibrium? Okay, so you already see, we already discussed this. Okay, so the condition of the static equilibrium is the first condition. There are two conditions basically. So the first condition is the net force is equal to 0. Okay, so net force F is equal to 0. Okay, so this is the first condition. Now, because force is a vector quantity and we cannot add the force acting in the x direction to the force acting in the y direction. Okay, so we can break this into two equations. So although this is one condition, but we have two equations. One equation is this, fx equal to 0, and another is fy is equal to 0. Okay, f equal to 0 can be divided into two equations, that is fx equal to 0 and fy equal to 0. Okay, so that means when we have a problem, when we are going to a static equilibrium problem, we have to add all the forces that are acting in the y direction together, and all the forces that are acting in the x direction, we have to add them together. Okay, and sum of all the forces along the x direction is equal to 0, and sum of all the forces that acts in the y direction, that is equal to 0. Okay, so for example, if we think about this problem, so this picture, okay, so here you see, for this picture here you see that we have a force, this force in the x direction, this force in the y direction. Okay, but then this force Fa is neither along the x-axis nor along the y-axis, so we have to break this force into its component to make them useful. Okay, make the component useful. Okay, so how to do that? In chapter 3 you already learn about that, right? So but if you forget, here let me review it again. So here, this is the force, okay, Fa, and this is the angle 60 degree. This angle is 60 degree. Okay, now if I want to break this force into its component, okay, I can draw a line from the tip of this vector to a horizontal line. Okay, so this is the horizontal line, this red line, and then from the origin, from the tail of the vector, I connect this vertical line. Okay, so this is one component, because this is parallel to the y, so this will be y component. Because this is parallel to the x, this will be x component. Okay, so once you break this, now we have two forces. So this force along the x-axis and this force along the x-axis, and then this force and this force are along the y-axis. So we have to add x forces together and y forces together. Okay, so that is the first condition of static equilibrium. So we'll be solving this problem in problem solving class. Okay, all right, the next thing we are going to learn is the second condition. So what is the second condition? Okay, so to understand this, let's consider this picture. Okay, so here let's say we have a ruler. Okay, and let's say there is a force F, let's say it is 5 Newton, and let's say another force in the other side, and it's also 5 Newton. Okay, so this 5 Newton and this 5 Newton are in the opposite direction. Okay, so this is in this direction, 1 5, and another 5 is in this direction. So the F net, or the sum of Fx equal to 0. So here you see that the Fx, basically we have two forces Fx, both are along the x-axis, so Fx equal to 0. But even Fx equal to 0, I mean the net Fx equal to 0, there could be a rotation. I mean this ruler can rotate about its center. Okay, so if it is rotate about a center, it is no longer an object under static equilibrium. Okay, so to avoid this rotation, we need another condition. Okay, so even sometimes the force is equal to 0, but the object can rotate. Okay, so to avoid rotation and still make it static equilibrium, we need another condition, and another condition is net torque is equal to 0. So if there is no rotation, I mean net torque equal to 0 means there is no rotation. Okay, so if there is no rotation, then we can say that the object is in static equilibrium. Okay, so the two conditions we have to maintain, one is the net force is equal to 0, and another is net torque equal to 0. And net force can be net force equation can be divided into two other equations. One is x equation, another is y equation. Okay, so for example, this is one example, this picture of static equilibrium. Okay, so to understand this, basically let me go to the simulation. So let me use this one. Okay. Now, so this seesaw board is now in equilibrium. Okay. So it's not rotating or doing anything. Okay. So now if I put one of the object here, so you see that it rotates. Now it is not as in a static equilibrium. I mean, you see that. Okay. So to make it static equilibrium, what we can do, we can take another and then put it here. Okay. So you see that now it is in static equilibrium. Okay. So here we have forces. Okay. So we have forces. One force is in this direction. Okay. The gravity for this one, and then another force is here. Okay. And also the seesaw board may have some mass, so there will be another force in this direction, and there will be also another force in this direction. This is the normal force. Okay. And then this is the gravitational force for the board, and this is the fire extinguisher, and this is another force for the fire extinguisher. Okay. So you see several forces are acting on the on the seesaw board. Okay. So these, and these. Okay. So we can show that the total force here is equal to 0. The net force, all are in the y direction, right? So there is no forces along the x direction. So that's a simpler case. So here you can show that Fy equal to 0, and you can also show that tau is equal to 0. Net torque is equal to 0. Okay. So we'll be solving some problem. Okay. Now, here net torque, when you determine the torque for each object, you know that torque is related to the force. For each force, there will be some torque. Okay. So we have to determine the torque for each force. Okay. So here you see that there are 4 forces acting on this seesaw board. Okay. Now, for static equilibrium problem, okay, you can choose any point as your axis of rotation. So if you remember, the definition of torque is something like this: tau equal to r f sine theta, right? Here F is the force and R is the lever arm. Okay. So for example, this is very simple, right? Because we already know the axis of rotation is this one. This is the axis of rotation. Okay. But for example, if we choose this one, the other one, okay. So here we do not know what is the axis of rotation. Okay. So now how to determine the tau? Okay. So here you have the choice. Okay. You can choose any point on the board as your axis of rotation. Okay. You can choose this as your axis of rotation. You can choose this point as your axis of rotation. You can choose this point as your axis of rotation. Okay. Any point. You have also choice to use this point or this point. Okay. No matter which point you are using to determine the lever arm, okay, the net torque will be 0. Okay. So this is the beauty of the static equilibrium. Okay. Tau equal to 0, but it is 0 for any point. Okay. So when it is in static equilibrium, you can choose the axis of rotation any point. Okay. So any point you can choose as your axis of rotation. All right. So yeah, we'll be doing some problem, and that probably help you to understand better. Okay. All right. Now let's go back to the slide. Okay. Now, next thing is the stability and balance. Okay. So here we are going to talk about 3 types of stability. Okay. So one is stable equilibrium. The next one is unstable equilibrium, and then the neutral equilibrium. Okay. Now to understand this, first let's consider these 2 pictures, this one and this one. Okay. So you see that this ball is on a bowl. okay, this small marble on this bowl. Okay, now this ball is at equilibrium, static equilibrium at this point, okay, because it is at rest here. Okay, now if you disturb it, okay, if you push little bit, okay, in this direction, it will go up and then come back, or if you push it in this direction, it will go up and then come back. Okay, so if we have an object something like this, okay, in an equilibrium, okay, so this object now is at equilibrium, and when you slightly push this object, push this marble, okay, you will see that it will come back, it will go up, and then it will come back to its equilibrium position. Okay, so if we have some situation something like that, we call it stable equilibrium. Okay, so another example is this one. So let's say this object, okay, is rest on this side. Okay, so now similar to this first problem, if you push it little bit, okay, you will see that it come back to its original position. Okay, so again, this is stable equilibrium. But now let's consider the middle two picture. So if we have some situation something like this, so for example, this marble is instead in static equilibrium on this ball, on the other side of the ball. But here, if you push the ball slightly, okay, in any direction, it will go down and will not come back. Okay, so it is at static equilibrium at this point at the middle, but if you disturb it, it will not coming back to its equilibrium position. Okay, so this type of equilibrium we call unstable equilibrium. So same thing here. Okay, so stable equilibrium, unstable equilibrium, and another equilibrium called neutral equilibrium. Okay, so if it is on a flat surface, okay, so if you disturb it little bit, it will find its new equilibrium. So this is its new equilibrium if you push it in this direction. If you push it in this direction, this is its new equilibrium. Okay, so if we some situation something like this, we call it neutral equilibrium. Okay, all right, so basically we'll be doing some static equilibrium problem. I mean, we'll be solving numerical problem using the static equilibrium, not this kind of thing. Okay, this is basically for conceptual background. All right, the next part of this lecture is about elasticity. Okay, so here you will be learning about elasticity, different kind of basically elasticity. Okay, and then fracture. Okay, so to understand this, let's first consider the Hooke's law that you learned in chapter 6 when you learn about the elastic potential energy. Okay, so Hooke's law tells us that if we have an elastic material, something like a spring, okay, so if you remember, so let's say this is our spring, undisturbed or unstressed or uncompressed spring. So this is its equilibrium position. Okay, now if you pull it, that means if you apply some force, you see that it is extended by this amount, delta x amount. Because of this force, this spring is extended by delta x amount. Okay, and we already see that the force, the applied force, is proportional to delta x. That means more the force, more the delta x. Okay, more the extension, less the force, less the extension. Okay, so that means delta x is proportional to the force, or force is proportional to the delta x, and then we can write that F equal to K delta x. And if you remember, K is called the spring constant or the spring stiffness constant. Okay, now even if the object is not elastic, not like a spring, even we have a metallic rod. So let's say we have a rod, this rod. Okay, so this one. So it also shows a similar property and more. Okay, so let's say we have a rod, metal rod, something like this, and you apply some force here. I mean, you add some mass here. So applying mass means, I mean, adding mass means you are applying some gravitational force here. Okay, so when you add some mass in this hook, you basically apply some gravitational force here. And experimentally, we found that because of the force you applied on the hook, this metal rod extended by some amount. Let's say it extended by delta L. Okay, it's very similar to the Hooke's law. So if you apply more force, okay, then this delta L, this extension will be more. If the force, the gravitational force is less, or applied force is less, delta L will be less. Okay, so we can write an equation something like this: delta L is proportional to the applied force. More the force, more the extension; less the force, less the extension. Is very similar to Hooke's law that you see in the, I mean, in case of a spring. But here we have something more. Okay, so to understand these, let's consider these pictures. Okay, so first let's consider number B and number D. Okay, so let's compare these two. So initially, let's say we have a rod, something like this. Its length is L0, and the cross-sectional area is A. A is the cross-sectional area, and initial length is L0. Now, if we apply a force F, okay, you see that the object A, this object is extended by this amount, delta L. Okay, and for the same force, okay, so if we apply the same amount of force, let's say it is 20 Newton. Okay, so let's say if you apply 20 Newton in this object, okay, in this rod, which is twice the length of this one, okay, you see that for the same amount of force, it is extended by two times. Okay, so this one's length was L0, it extended by delta L. This length is 2L0, it extended by 2 delta L. Okay, so what it means? It means delta L, the extension, is also proportional to L0. If the initial length L0 is long, then delta L will be long. If L0 is small, delta L will be small. Okay, so that's the two condition. Okay, now let's again consider B, and now with C. So I'm going to compare these two. Okay, so you see the B is the original, I mean, it's very similar to this one. And now C has the larger cross-sectional area. So the cross-sectional area for this one is A, the cross-sectional area for C is twice A. Okay, now if we apply the same amount of force, okay, similar to the last problem, if we apply 20 Newton, for example, you see that this one is extended by delta L, but this one is applied by extended by half of delta L. Okay, and this tells us that extension delta L is also depends on the cross-sectional area, but it is not proportional, it is inversely proportional. The more the cross-sectional area, less the extension. So here you see that for the same amount of force, in number C, the extension was half. Okay, so that means it is inversely proportional. Okay, now if I combine these three equations, I can write these. Okay, or if I remove this proportionality sign, I need a proportionality constant. Here, this is the proportionality constant. So E is the proportionality constant, and this E is basically the properties of the material. So if it is made of steel, E will be different than if it is made of, let's say, copper. Okay, so E basically tells about the property of the material. Okay, so E is called, so here E is the elastic, is a proportionality constant, and it is called the elastic modulus or the Young's modulus. okay, and its value depend on the material. For different material, the value of E are different, okay, but it is a constant. Okay, so in the table here, I'm showing some elastic or Young's modulus for some of the materials. So here you see that for iron, it is 100 times 10 to the power 9 Newton per meter square, and steel it is 200, and so on. Okay, so we are going to also learn about shear modulus, bulk modulus next. Okay, so here you see that this table shows all, but in next slide you are going to learn about more on shear and bulk modulus. Okay, but before I go to the shear and bulk modulus, let me talk a little bit more about the elastic modulus. Okay, so in the last slide we see that delta L is proportional to F, the applied force, right? Now let's draw this graph. Okay, so I mean, this is basically experimental graph. So here they use force in the y direction and the elongation or the extension in the x direction. I would basically do opposite. I basically do delta L in this direction and F is in this direction. But anyway, so this I copied from your textbook. So whatever they use, let's go with this. Okay, so it is a force versus elongation. Okay, now here you see that as you know already, that delta L is proportional to F. That means more the force, more the elongation. Okay, and there is a property here also similar to the elastic property, similar to spring. Okay, so when you release the force, okay, it goes back to its original equilibrium position. Okay, let's say you apply some force, it extends by some amount. When you remove this force, okay, it goes back to its equilibrium position. The same thing happened here also. If you apply a force in the hook, okay, it extended by some amount, and then when you leave this, when you remove this force, it goes back to its original position. Okay, so that means F and delta L are proportional to each other. Okay, so here you see that for this force, this is the delta L. For this force, this is the delta L. So you see that at some point it violates, right? So here you see it reaches, when it reaches to some limit, it violates. It's not proportional to each other. Okay, so this is valid. I mean, this proportional relation is valid at some point, at some limit. Okay, after the limit, it doesn't basically work much. Okay, this equation is not valid. Okay, so this equation is valid until certain limit. Okay, so before it reaches to that limit, we call that region as elastic region. Okay, because material behaves like elastic material. When you apply, I mean, within this region, within elastic region, when you apply force, it extends. When you leave this force, it goes back to its original position. Okay, so this is the elastic region. Now when you reach the elastic limit, and then if you still adding forces, okay, you will see that there is extension. Okay, there will be some extension, but when you reach or when you pass that elastic limit, if you remove the force, it will not go back to its original equilibrium position. Okay, so the object goes back to its original position if it is within elastic region. Okay, after that it is extended. Okay, when you apply force, it will extend more. If you apply more force, it will extend more, but it will not go back to its equilibrium position. Okay, so at this point, it will be behaving like a plastic bag. Okay, so you know that when you pull a plastic bag, it extends, but when you release your force, when you remove the force, it will not go back to its original position. So object behaves exactly same thing like that. Okay, so that's why we call it plastic region. So when the object or material enter this region, when you apply force, it extend, but when you remove this force, it will not go back to its equilibrium position. So we call it plastic region. Okay, and plastic region has also has some maximum limit. Okay, so if you keep adding forces, okay, at some point the object will break. Okay, so when it breaks, we call it breaking point. Okay, so breaking point is related to the fracture. Okay, so we are going to learn about fracture at the end of this chapter, in the next slide, I think, or in the following slide. Okay, so you see that in this region, in elastic region, object behaves like a spring. That means you apply force, it extends. Okay, when you remove this force, it goes back to its original equilibrium position. After elastic limit, it enters the plastic region. In plastic region, you apply force, it extends, but when you remove the force, it will not go back to its original equilibrium position. It behaves like a plastic. And if you keep adding forces, at some point the object breaks. Okay, and we call it breaking point. And this breaking point is related to the fracture, which we are going to learn next. Okay, all right. Now, before I talk about fracture and other types of modulus, okay, let me introduce some terminologies. Okay, so the first thing we are going to learn is stress and strain. Okay, so what is stress and what is strain? So stress and strain, to define stress and strains, let me start with this equation. The equation we derive in the last slide, delta L equal to 1 over E F over A times L0. Okay, so if I solve it for E, it gives me something like this: E equal to F over A L0 by delta L. Okay, now let me simplify a little bit. No, I don't need to simplify, so that's enough. So here in this equation, F over A is called stress and delta L over L0 called strain. Okay, so E, the elastic modulus, is basically stress. So F over A is stress, and this is 1 over strain, right? Strain is delta L over L0, but here we have L0 over delta L. So what we have here is 1 over strain. So elastic modulus is equal to stress over strain. Okay, all right. Now, if the force here in this equation is due to the tension, okay, so you already know that what is tension force, right? So if the force is tension force, I mean, if you are pulling this object, okay, so you are pulling this object, so this kind of force we call the tension force. So if the force is tension force, the corresponding stress and strain we call the tensile stress and tensile strain. Okay, but if the force is due to the compression, so here you see for this one, it is due to the compression. You are compressing this object. So if the forces are due to the compression, then the corresponding stress and strain we call the compressible stress and strain. Okay, for example, in this picture, all the beams are under compressible stress and compressible stress. So this beam, this beam, this beam, okay, these are under compressional stress. Okay, because they are compressed by this force. Okay, all right, the weight of this force, I mean weight of this mass, basically weight of this mass. All right, next we are going to learn shear stress and then change in volume, and then fracture. That's it for this lecture. Okay, so few more things. So what is the shear stress? Let's say, to understand shear stress, let's say we have an object something like this. Okay, now if you push it, okay, it will be under compressional stress. Okay, but instead, if you, instead of pushing it downward, if you apply force something like this picture, okay, then you see that the shape of the object changed. Okay, so the object deformed from its original shape. Okay, so if we have something like this, we call the object is under shear stress. Okay, so shear stress is exactly can be defined from this equation, delta L. So we have already this equation, right? F over A L0. So from this equation, we can define the shear stress, but the definitions are a little bit different here. Okay, so here we use elastic modulus. So this is shear modulus. So in the table earlier I show you, you already see that there is a column for shear modulus and then bulk modulus. So this G is the shear modulus. Okay, now how to I mean, what I wanted to tell you is what are the meaning of all these. Okay, although it's very similar, but the meaning of A and L0 are different than A and L0 in tensile and compressional stress. Okay, so what it means, F is easy to understand. So here you apply a force F. So this is the force. Okay, but what is the cross-sectional area? What is A? A is not this type of cross-sectional area. So A is the area on which the force is applied. So for example, for this problem, for this picture, force is applied in this side. Okay, so A means the area of this side. So for example, here the force is applied here. So the area of this is A. Okay, A is the area of this. Okay, now what is L0? Now don't confuse, L0 is this one. Okay, L0 is this length. Okay, it's basically um, um, the length of the side. I mean, it's basically the distance of two opposite side where F is applied. Okay, so F is applied here on the top side. Okay, now we have to determine the length from this side to the other side. Okay, so this is L0. All right, so A and L0 are this, but what is delta L? Delta is the amount of deformation. So for example, here the amount of deformation is this. Okay, this amount. So delta L is not the extension or the compression. Here it is the amount of deformation. Okay, so that's the difference. Although the equations are very similar, the meaning are different. Okay, so delta L is not the extension or the compression, it's the deformation, amount of deformation. Here G is the shear modulus, F is force, it's easy to understand, E is the area where the force is applied, and L0 is the length of the two opposite side where the force is applied. Okay, all right. The last thing is the change in volume. Okay, now let's say we have an object. Okay, so the inside object here. Okay, and we submerged it in a liquid. Okay, so when we submerge something in liquid, the object feels pressure from all the side. Okay, so it feels basically force from all the side. Okay, so because of the force from all the side due to the liquid, its volume changes. Okay, so Then in the last two situation, we see that the length changes or length deformed. Okay, here the volume changes. So by looking this, delta L equal to 1 over E, and then F over A, F over A original length, we can write the equation for change in volume. Delta V is equal to, so we replace E by B, okay, F over A, but now L0 is not, I mean, because this is the change in volume, we need the volume, original volume, okay, and we should have a negative sign. Okay, let me tell you why we have a negative sign here. Now when you submerge something in a liquid, volume decreases because of the pressure from all the side. Okay, so this minus sign we have here because of the decrease in the volume. Okay, so in this case, when change in volume happens, basically most of the time the volume decrease. Okay, so when you deal with delta L, okay, either the length increase or compressed. Okay, but here most of the time delta V volume decreased, volume decreases, so that's why we have a negative sign here. And B here is the similar to the elastic modulus, we call it bulk modulus. And in the table I showed earlier, you probably remember that there is a column for the bulk modulus. Okay, so this is very similar to the Young's modulus. And F and A, the force per unit area, and V0 is the volume. But here when we deal with the liquid, we do not use F over A. Okay, F over A is basically the change in pressure. Okay, delta P. Okay, so change in pressure is delta P. So instead of this equation, we write something like this: delta V equal to minus 1 over B delta P V0. Okay, or we can simplify this little bit by writing this equation as this. Okay, all right. Now the last thing is the fracture. So when we talk about the elastic region and plastic region, you see that for some force, okay, object breaks. Okay, so the breaking point, when the object reaches the breaking point, object basically fractured. Okay, now fracture is related to, for each object, fracture is related to something called the ultimate strength. Okay, and ultimate strength is defined as this equation. Okay, F max over A. Okay, so ultimate strength of each object, ultimate strength is basically a constant number. Okay, for a material, okay, it's a constant number. For example, we have ultimate strength for iron, for example. So let me show the table here. Okay, so for example, you see that iron cast, we have ultimate strength. Okay, but ultimate strength is different if it is tensile force or if it is compressive force. Okay, so ultimate strength also depends on whether it is a tensile, under tension, or under compression, or under shear. Okay, so depending on that, it will be different. So you have to understand the situation. When there is a problem, make sure you understand whether the problem is talking about the tension force or compression force or shear force. Okay, depending on that, it will be different for different material. On top of that, it also depends on the cross-sectional area. Okay, so ultimate strength, let me call it U as ultimate strength, and that is equal to maximum force and cross-sectional area. Okay, so that tells us that for different cross-sectional area, maximum force will be different. For example, let's say we have a two rod, one is like this, okay, and one is like this. Okay, they made of same material. okay, and the same length. If they have the same length and they made of same material, okay, although the ultimate strength is same, okay, ultimate strength is basically a property of material, and let's say both are under tension, okay, then the maximum force will be different for the different object, because here you see that cross-sectional area is higher than this, okay, because the cross-sectional area is higher for this object, okay, we have max, the F max will be higher than this one, okay. All right, so that's the ultimate strength, okay. So ultimate strength means at that point the object will break, okay, I mean object will reach to the point where it break, okay. Now when we design a structure, okay, so for some student it needs to, I mean, who are architect or engineering major, okay, if you design a structure, you should keep in mind that the anticipated stress should be less than 1/3 to 1/10 of the ultimate strength, okay. So if you or career if you follow the career where you have to design a structure, make sure you understand this, okay. So if you design a structure, remember that ultimate strength and the anticipated stress should be 1/3 to 1/10 of the ultimate strength, okay. All right, so this table here, I already talked about it. This table shows us some number, okay, for different types of forces, okay, at which those object reaches the ultimate strength, okay. All right, so with this I'm going to stop it here, and in the next lecture I'm going to solve some problem, okay.